Welcome everyone. So, in today's class we are going to discuss about some recent advances in C-based VLSI design. So, we are at the end of this course and we have already learned so many things in high level synthesis or in C-VLSI VLSI design. So, I am going to emphasize the things that is happening in last 2-3 years in the context of C-based VLSI design. So, there are 5 areas which is very active in terms of research in VLS design. They are basically security, hardware security in context of high level synthesis or VLSI design, verification of this whole process, and then hardware acceleration for machine learning and domain specific high level synthesis and automation for high performance hardware accelerator generator. Okay. So, these are the 5 areas in my opinion is very active domain of research in context of C-based VLSI design. So, what I am going to do is I am going to just take each topic at a time and I am going to talk about what are the recent works and what are the kind of things happening in that particular domain. Okay. So, let us start with hardware security. So, we have already discussed in this course itself that because of this fabless production of the ICs, your IP or intellectual property of the design house goes to third party, and there may be some rogue employee there or some untrusted employee there. They might steal the IP, they can do some overproduction or they can do IP piracies. And to stop that, the logic locking is something a very popular technique and is very novel technique evolved, right. And in this course also we have discussed that this logic locking is basically nothing but you add some extra key in the circuit and you give that locked circuit to third party, but do not give the key. When you ship that whole IC, you just store that particular key in a non-volatile memory and you just give that IC functional IP to customer. Since that correct key is already there in the functional IP, so it will give the correct output. But since that locked circuit which that untrusted employee, untrusted component access, he does not have the access of the key, he cannot use it basically, right. So, that is the idea of logic locking, and we have seen that there is a plethora of work happening in the gate level logic locking. So, how to lock the circuit at the gate level, how to break it and so on. And then there are recent work specifically this tau and host that is mentioned here is basically try to do the logic locking at the time of high level synthesis. Okay. Specifically tau says that if I give a C code, I am going to give you RTL code which is locked with some extra key, maybe 200, 500, whatever the number of keys, and host is basically take the RTL which is generated by high level synthesis and you try to lock that RTL circuit. So, it is basically not during high level synthesis, but it is basically at the end of high level synthesis, but this host supports only RTL which is kind of generated by high level synthesis tool. Okay. So, these are the some recent work on the locking the circuit during higher level of abstraction or during high level synthesis. And also as I mentioned in during discussion of the course that whenever you come up with some kind of locking technique, always there is a scope of checking whether the locking is robust or not, right. So, basically there are some attack methods also evolved, right. So, in the recent work is a SMT attack which basically proposed in this paper which basically can break tau. Okay. So, and then basically as a and then this host evolve which basically say that this SMT attack cannot break this host, right. So, whatever the drawbacks that SMT attack identify in the tau, it basically resolve those issues, right. So, this host is a technique where you cannot apply this SMT attack directly. Okay. So, this kind of work is happening in this domain. There is, and I mean actually have covered all this I mean tau I have covered, SMT attack I have covered, host I have not covered, but that is something is similar to in tau line. Okay. And another important aspect in this hardware security is the information flow tracking, right. So, and is very well researched area, right. So, is basically you have a circuit which is happening, you have a processor which is running and you try to see is there any secure data is going to some to unsecure component of the whole processor, right. So, basically there is a flow of information from higher security to lower security objects, okay, and which is very common, and there are plethora of work is happening again here in the context of processors, hardware and all. So, and then basically in this particular work, this Tent-HLS, what basically is try to do that I can actually generate a RTL which is from a C code, which is the RTL plus the information flow tracking things already embedded into the RTL. So, I have a now RTL which is generated by a high level synthesis tool from a input C code, and but in that particular C code can also that particular generated RTL can actually track the information flow, right. So, the basic idea is like this. So, you have the data path and it actually add a shadow circuit. Okay. So, this data path is say maybe 32 bit, 42 bit with data width, but this is a 1 bit kind of. It is basically you have to just check yes or no whether a sensitive data flow to a unsecure component, yes or no, right. So, it is kind of a boolean. So, this is actually the data path. And then this is the overall architecture. Then basically you have this common data path and it is automatically at the shadow data path where you actually take the information flow, and the whole thing is basically have a controller which control both, and then this data also come back to the memory. You just store this tent value, and whenever you kind of have some kind of tent is basically the information flow. Whenever there is a you identify there is a violation of information flow from higher to lower security, probably you can actually give a kind of alarm signal, right. So, that information flow tracking is not something new, but what is new is basically how we can actually generate a circuit which is kind of auto, which is kind of can track the information flow within the circuit itself. Okay. So, that is something again another interesting work. So, this is what is happening in context of hardware security in high level synthesis, and now let us move to the next one. And this another very important, very live, very active area of research is verification of high level synthesis. So, we have seen that this whenever you generate a RTL from a C code, because of the complete different semantics, different way of execution of this behavior, so checking functionality whether the generated RTL is functionally equivalent to the input C code or not is extremely important, right. So, there may be some bug introduced by many reasons. Okay. There are two ways we usually verify, is simulation or formal verification. And in the context of formal verification of high level synthesis, till now there is no automated for end to end formal verification tool, does not exist basically. Okay, which basically take the C code and RTL without taking any information from the tool, it just check whether they are equivalent or not. So, that still is evolving, right. So, we do not have any very mature tool there. There will be some paper proposed, but they are not something robust enough to handle all kind of optimizations that high level synthesis tool offers. So, in the context of formal verification, so most popular approach is basically phase wise verification, and I have actually covered this both the topic in this course. And then we have seen that basically among all these verification steps, scheduling verifications is basically the most important, and the most kind of decision has been made during scheduling. So, verifying scheduling is very important, and there are a lot of work is happening. I just cited here one of the recent work from our group, but there are, if you just go into this, you will find many such papers is coming on this phase wise verification of high level synthesis. On context of simulation based verification, again basically we have to simulate the generated RTL with some input. I have to simulate the C code with the same input, and I just compare whether this they are giving the same output or not, right. So, that is the kind of simulation based verification, and I have already explained in this course itself that this simulating RTL is much slower than the simulating a C code, right. So, because this RTL is basically RTL simulator is cycle accurate, lot of detailed information of the data path controller. So, it has to go through all things. So, it is basically slower, and in general it is basically 300 times slower than the C simulator, because C simulation is done with say any C compiler like GCC or LLVM, whatever it is. Okay. So, that something is little bit bottleneck, and so this the recent works try to do it is basically try to do a fast simulation of high level synthesis. Okay. So, the basic idea this all this recent work is happening is basically you try to extract a C like behavior from this high level synthesis output, and then you try to simulate using the C compiler, right. So, then it will be faster, 300 times faster, right. But you have to make sure that your generated C code is not the input C code, rather it is a cycle accurate, it is a cycle accurate C code, and it actually can give a performance estimation, you can give all the things that this RTL simulator gives, right. So, you have to make sure that those are the features is available in the generated C code. So, in this there are two recent work which is very important in this context, one is Flash and one is FastSim. In the Flash, what it does is basically it generates a C code from the schedule after scheduling, okay, because it just argued that because once you do the scheduling everything is fixed, right. So, it basically take the intermediate information from the tool after scheduling, and from there you just generate a schedule C code and then it simulates, okay. So, that is what is this Flash does, but as I in that argued in this particular paper FastSim, which is from our group, is basically if you just verify this, it only verify the scheduling, it does not verify the allocation binding or the data path control generation phase, right. So, and also it has to take some intermediate information, right, scheduling information that may not be available also in some cases, right. So, what FastSim does is very important and very I would suggest that is very does a very important job in the context of simulation based verification, is basically it does not take any intermediate information from the tool, rather it takes the output RTL and from there it generates a C code, okay. And that it actually shown in this paper that it is basically cycle accurate, it can give a accurate performance estimation, it can handle all the optimizations that the modern high level synthesis tool offers, and then you can use that particular C code for faster simulation using C compiler. So, I have already covered the basic intuition of FastSim. So, basically you have a RTL to C converter, right. So, that I have already discussed in this class, and so with that we can show that we can actually do this simulation based verification of high level synthesis very fast, okay. So, this all about this verification of high level synthesis. I mean there are a lot of research to be done in this front, I would say, and also in this spaces also there are so many complexities are there which is not get handled by the current the synthesis tool like this data flow, systolic array implementation. So, many things is happening internally which is not supported by this particular existing works, right. So, we have lot of scope to work in this formal verification context of high level synthesis, okay. So, let us move on. The next one is basically to do a kind of hardware generation for machine learning algorithms, which is done by tool LeFlow. So, basically if you write, how do you write the machine learning code, right. So, we usually write in TensorFlow, right. So, we have write our code in using Python in TensorFlow flow, and then we have that code and we use it for training and other purposes, right. So, now our objective is to try to generate a high RTL for that particular TensorFlow code, right. So, what we should do now? We have to manually write the corresponding C code, right. So, because the TensorFlow code is very high level code, it has some APIs, you just use it and you just use the API for convolution and so other operations, right. But here you have to manually rewrite the corresponding code in C, then only this high level synthesis tool can take it on, right. So, what this LeFlow does is very interesting, is basically does not evolve any new high level synthesis tool, it just use the existing high level synthesis tool called LegUp, right. What it does is basically take the TensorFlow code, use Google XLA compiler and convert that TensorFlow code into some IR, LLVM IR or some intermediate representation, okay, and from which this high level synthesis tool can understand, right. So, basically if you understand the high level synthesis tool, what it has basically have a C compiler at the start, right. So, which basically take that C code and convert into some IR, right, and from that IR the convention process goes on, right. This scheduling, allocation, binding and all the phases has gone. So, now the point here is that if you have some way you can just represent the TensorFlow code into this IR form, then high level synthesis tool will understand that, and that is what this tool does, right. So, it basically the flow is like this, you have this Python program and then it use the XLA compiler of this Google, and it basically generates some IR which is LLVM, right. LLVM is another C compiler. So, it can be GCC, for example, if it is VLSI, it basically understand the IR which is generated by GCC, but there are other tools like LegUp which basically understand the LLVM IR, and this is nothing but this HLS tool, right. This is nothing but HLS, right. So, what it does is basically convert this into IR, but what this LeFlow does is very important. So, this IR what it generated from the TensorFlow code. So, high level synthesis tool does not support many of this IR. Okay. So, basically Excel will give you IR. So, then you might ask that what is the other things to be done, right. So, you generate IR and then use the leg up, but the problem here is that there are several transformation to be made in the IR to make it seamless interface between these two. So, basically it does not that whatever the IR did generate that a leg up understand, right. So, you have to understand certain IR which does not is synthesizable, or say it does not leg up does not understand those syntax. So, you have to convert those IR into some equivalent representation, right. So, that is what this LeFlow does. It identify those gap between this IR versus the IR it understand and basically bridge the gap, right. So, with this is basically open source tool, and basically you can from any TensorFlow code you can generate the hardware what you want, right. So, you can actually follow this paper and the tool is given in this particular link. Okay. So, this is about creating a flow from this TensorFlow code to RTL. Okay. So, we will discuss by end of this class that we need to do some more to generate a efficient hardware. This actually give you a flow, right, from this TensorFlow to RTL, but it does not give you the efficient hardware always. Okay. So, we need to do something more on this context, and that is what is basically addressed in other works. I am going to talk about that. Okay. So, before going to that particular topic, I will just cover another aspect which is basically domain specific language and synthesis. Okay. So, this something is very important, because if you consider specifically the image processing or video processing domain, right. So, we have basically lot of data comes, lot of image, lot of video comes, you do some kind of processing, right, you identify age or you do some other kind of processing, and then you basically and that processing is nothing but a nested for loop and doing some operation, right. So, there is a computation which is basically embedded in a nested loop, right, that is all, that is what is this particular application demands. Okay. But here the problem is once you when we have already discussed in this course as well, that once you try to synthesize this particular application for efficient hardware, the problem happens that you have to manually modify this code little bit, right. So, not little bit, or maybe you have to try different way, right. So, sometime you said do some loop reordering, you can do some loop splitting, you can do some loop interchange, and so many loop of kind of optimization you can do, and you kind of generate different version of the code, and then you synthesize and see which is basically goes well in hardware. Okay. So, basically here you have to do all those things manually, right. You do the loop splitting, you write the C code, you take the some matrix multiplication, say for example, and you basically do some loop tiling, you write another version of the code. Okay. Say for example, I just give an example here. So, this is a blurring example where you have this x and y, and this is the actual computation is happening, right. So, you have some array, you are just taking some value and then you calculate something, and then you do again this way. Okay. So, the point here is that we are say suppose you understand that if you just do the interchange of this loop. So, basically you bring y first and then x, here x is first and then y, here it is y first and x in both cases. So, here by doing this transformation, the locality of reference actually improves, and you actually can generate 15x faster hardware, okay, in terms of latency. So, this is something if you have to do, you have to take this code, you have to rewrite into this, right. So, this is a very simple example. So, but if you understand that internally this computation remain the same, right. So, I do not change anything for this computation part. What I just do? I just do change the schedule, right. So, how in basically this if you just interchange this for loop, there are say n square xy operations happening, right. So, the order of this operation gets changed, that is all, right. That means the schedule of this execution of this operation basically gets changed, right. So, this particular domain specific language basically does a very important job. What it does basically, it just decouple this algorithm from the schedule. Okay. So, whatever the way you do, whether the way you write this version of the code or this version of the code, computation remain the same. I am not changing anything here, only thing I am doing is just changing the schedule. So, if you just separate this schedule and computations, then what will happen? I do not have to rewrite this whole thing, right. So, what the basic idea here is that you basically specify your computation first and then you have some option where you specify which kind of scheduling strategy you want to use. Okay. So, basically it separates out this decouple this algorithm from schedule, and algorithm is what is exactly get computed, that what I just mentioned, schedule when and where it get computed, right. So, for example, here if you just interchange y and x, the way it is basically this value will be computed, it will be different, right. So, for example, here if it is x and y, so basically you can say that 0 0 location will be computed, then 0 1, then 0 2, right. This is the order of blur x y, right, then 0 3 and so on, right. Here what is going to happen, since it is y, so it is basically 0 0, then it will be 1 0, then 2 0, it is the first row, right, this is the first column. So, but this is the, so order is getting changed, right. So, this is what the impact. So, this is basically Halide is a kind of a language which basically allow you to write your code where you can separate out this algorithm and schedule. Okay. So, it has language, I am not going to detail of the language detail. So, what you can do, you can just say in blur these are the two computations, right. So, if you go back to this blur example, there are two computations, this is the computation 1, this is the computation 2, right. So, in this Halide language, instead of writing this for loop or this for loop, you just mention that actual computation is this 2, and then here you specify whether you want to execute x first, x loop first or y loop first, what is the range of x y, whether you want to do a tiling, whether you want to do a vectorization. So, for example, here what it is just basically you do these computations for say 256 0 to 256, but you do a tiling, right. So, you just do a tiling where you basically break this loop into 32, a tile of 32, where you use the x I and y I as the tile, and then also within that x I you do the vectorize by of 8, you try to do a vectorized execution of this x loop, and you just parallelize this y, right. So, you just specify all those things using this comment, right. So, this is the language where you can just specify, instead of writing that C code, this C code I am going to just write this, right. So, I just specify what is my computation and then what are the optimization I want to use, right. If you are a very experienced user, you know which kind of optimization I should use, so that this particular loop will be have efficient hardware, right. So, so basically once you do this, what Halide does is basically it is a compiler, it actually generate this actual code, right. So, this is the C code you want, where you actually have a tiling, you see you have this is the y tile, this is the x tile, and then you have this loop which is basically divided into tiles, you just do the vectorizations. So, all this whatever the things you want is get implemented, right. Similarly, this is the next one where you apply this optimization, and because of that this is happening, right. So, the Halide is basically is a very important and powerful concept in my opinion, because it's basically reduce your effort, because you do not have to now anywhere you have to write this version of the code, right. This writing this version of the code need lot of effort, rather you just specify what is the computation, you specify what are the optimization you want, and then you give it to Halide, and then it will automatically convert this into the code that you want after applying this optimizations, right. So, this is what Halide, it give you a language to represent certain your computations and the optimizations or the schedule you want, and it has a compiler inside which is basically apply those optimization on the computations and it give you the C code you want, right. So, this is very interesting and very useful tool. Okay. So, the tool is available here and you can actually try, right. So, it is your examples. So, now the question is that once you generate this code, how do you synthesize it, right. So, here you can see here you can probably apply this, you have to do this the basic, there are two options. One is basically you can actually rewrite this whole Halide program into domain oriented, domain specific language for hardware oriented DSLs, domain specific language such as darkroom, soda and all. And then you use that, you basically that will allow you to basically represent things in hardware, or you basically use high level synthesis to generate hardware, which is very easy, right, because this is nothing but a C code, right, C or C++ code. So, from there I can use any high level synthesis tool to generate the hardware, right. So, this is what this Halide-HLS and Hetero-HLS does, right. So, basically this Halide-HLS is again it's take this synthesizer C code and it takes some existing high level synthesis tool. You do not have to develop another high level synthesis tool and you generate the Verilog, right, the RTL. Again this Halide-HLS available here, the detail of these things you can get in this paper, and then the overall flow is basically you have this Halide code, you have this tool which is basically generate this that IR, and then you basically can use the high level synthesis tool to generate the RTL, or you can actually synthesize same thing into processor, right. You can run the same code in a processor using that C compiler, right, or C++ compiler. So, that is all about this. It is a domain specific language, it is very important and powerful area, and whenever you develop something in that context, you have always option to convert them into RTL using high level synthesis. Okay. So, where this Halide-HLS or high level synthesis will be useful in on top of domain specific language like Halide. Okay. So, let us move on. So, as I mentioned when I just talk about this LeFlow, that although this LeFlow give you a option to generate a hardware from this TensorFlow code, it does not have any kind of power to give a very efficient hardware, right. So, and this is already I have discussed in this course several times, that once you have a code, specifically the nested loops is something where you have to give your maximum attention. Array access, this is where you have to give a maximum attention. You have to make sure that you can have a efficient synthesis of those loops and arrays, right. And the things that we have understood in the class also with the matrix multiplication example, that once you have a big computation is happening, if you just do it sequentially, you are not getting the power of this hardware. Specifically in the FPGA, if you think about, there are a lot of CLBs, they are actually running in parallel, right. Lot of DSPs running in parallel, lot of RAMs are running in parallel. So, unless you do kind of parallelize, right, your input C behavior, you will not get the performance. So, for efficient hardware accelerator generation, that is must, right. So, you have to somehow parallelize your input behavior, right, and that is what is basically is known as either temporal to spatial conversion. So, spatial is basically parallelized, or also it is some form of systolic array generation, right. So, it is basically you have an application, you try to parallelize, you basically find out some component, the basic unit component there, and you try to execute those components in parallel, right. So, for example, if I just recall my matrix multiplication example again. So, it is basically two matrix gets multiplied, right. So, one row multiplies one column and I get one element, right. So, basically for one element there are n multiplication needed, right. So, and but to do this I have to access the complete row and complete column, right. So, what I can do, I can actually break this into small component, and I can just do this part of this computation one time, next time I will just do this component with this time, then next time I am going to compute this with this time, right. So, or in this way, sorry. So, I can actually split my whole array into this small component, and basically you have a multiply and accumulate operation is happening, right. So, I can actually do this and this one time, and then I can do this in parallel, and so on, right. So, the basic idea of this efficient hardware generation, this is the architecture you want in the hardware. So, you have to identify what is the what is the minimum, what is the actual computation happening, just like in matrix multiplication, basically multiply and accumulate, and you can actually break the whole computation into small component, right. So, you just break into a smaller component, and you can actually connect them in a systolic array format. So, that you can actually propagate the data through one component to another component and so on, and then run all this P in parallel, right. So, you run all this P in parallel, and then only we will get a maximum benefit, and this is what is called systolic array architecture, right. And then basically your data is in some outside memory, and you actually fed them through FIFO channel to this in the hardware accelerator, and where you store the small component in the memory in a say local RAM, right. So, this is the loader, and also the output you can actually put in another RAM, and you can actually serially go into outside. So, if you just try to can map your application into this kind of architecture, then only you will get a maximum benefits, right. This is what you want at the hardware level, which is basically efficient. Okay. So, so this is what I want, and then the point here is that I have given a sequential example, right. So, I have given a sequential behavior. So, the question is how I can achieve this, because this will result in me in a very efficient hardware. Okay. So, how can I generate this? Okay. So, for that there are 4 tools are available. So, there are tools called AutoSA, T2S, Hetero-Halide. I am going to talk about all of them in briefly. So, there are 2 avenues of approach here. The first approach is that is basically just like Halide. This tool allow you to write your computations and the schedule differently, right. So, it has option to specify tile just like Halide, you how to vectorize, how to parallelize, those comments are there, and you have the computations, and then this tool just like Halide compiler, it can generate this kind of architecture, right. So, that is one approach, and this 3 tool is basically on that domain. AutoSA is basically try to automate this, right. So, it does not ask you to rewrite your application in a specific language just like Halide. What it does is basically you text your C code, you does some kind of this analysis, and it generate this kind of systolic architecture. Okay. So, let me just go through them one by one. So, in the Hetero-CL, what I just talked about is basically similar to Halide. It is basically decoupling this algorithm from hardware customizations, right. So, the example that I have given here, there are say algorithm 1 you need this kind of customizations, algorithm 2 you need this kind of customizations, and algorithm 3 you have something else. So, what you can do is just specify the algorithm as a computations, and then you specify all the customization you need in together, right. So, this is similar to this Halide, right. So, here is an example. So, so you just specify your algorithm here that you have this is the range, and you try to compute this, and then you specify here that you split this particular x with a factor of m, you reorder this xi with reorder xi and xo, and you generate this, right. So, this is the I am not going into detail of the language, but this is similar to Halide. You can understand that you specify your computation, you specify your optimization that you want or the customization you want, and it basically generate this code for you, right. This is what this Hetero-CL does, right. So, and this is basically is when you try to synthesize it in hardware, you will see that this actually can generate this kind of architecture. Okay. So, this is what Hetero-CL, and then from there you have option to go into RTL, right. So, this is the overall flow here. So, you have option to specify this in the Hetero-CL language, and then it basically or internally convert into that IR, which is basically after applying this optimizations into this code, and then in the back end you can actually use the LLVM code generator, and you can go to CPU, you can run in CPU, or you can actually go into some high level synthesis tool like Vivado or Intel tool, and you can run it into FPGA, or you can actually from this code you can apply AutoSA, I am going to talk about that, or T2S, and you can generate things for FPGA, and also you can write some domain specific, you can represent this in some domain specific language in hardware level, and you can run it in some embedded or cloud FPGAs, right. So, this is the overall flow of Hetero-CL, but the basic idea here again is this applying this kind of optimizations, creating a systolic kind of architecture from a C code is something is kind of achieved here. Okay. T2S also similar thing is basically again is similar to Hetero-CL, that you have this in the FPGA board there are so many parallel blocks, right. These are the CLBs, and they are connected, and some of them as DSP, some of them are ALUs and all. And so, basically if we can break my whole behavior into this kind of small component that I have shown in the previous slide as well, and then I can map them into in parallel modules, right. So, this is the idea, right, and then you have this L1 cache, L2 cache, which is to manage this locality of reference of data, right. So, this is what basically we need some. So, basically you have a sequential code or temporal code, you have to convert into spatial, right. So, that is what this tool does. Okay. So, basically what is happened here is that you again it has option like you write the computations, and there is option to specify the optimization that you want, like tile, unroll and all. It is similar to Halide again, and then this tool convert them into this parallel architecture, and then using again the same thing, this either OpenCL-HLS code or LLVM, you can map it to CPU or FPGA and so on, right. So, this is what this T2S does, similar to HLS. Okay. And Hetero-Halide is the same thing, that you basically convert this Halide code into Hetero-CL code, and from there you can actually use that Hetero-CL-HLS to generate into RTL, right. So, again the code base is available here, and you can go to this paper to understand more about Hetero-Halide. So, these three tools are of different same type, right. AutoSA is something is not you have to specify your algorithm in a different language, just like Halide. Here it is basically given the C code, and it automatically generate this kind of parallel architecture, right. So, this is some component, processing unit, processing elements, and then they are actually connected in a systolic array format, and then you have this all this memory support FIFOs and also locality of references, and then this is happening, right. So, what it does is basically the detail is in this paper, you can go through it, and it basically does this. Basically, it has do a polyhedral analysis, right. So, it basically create a polyhedral model from this, and then it just try to do a computation management and communication management. So, basically if you go into this diagram, this is the computation happening here, and these are the communication unit, right. So, you have to from this code you have to understand what is the basic computations. So, that is the computations, and this is where this computation is happening, and then you if you just break the loop, your communication gets changed, right. So, communication in that the flow of data, right. So, which data I need first. So, this is a matrix multiplication example, right. So, it is basically manage this try to break this whole computation into small unit, and then you try to make sure that you have the data flow, data is ready, and the interconnections is according to the data communication needed by this kind of architecture, right. This is what is systolic array design. Okay. So, this is the overall tool, and it just kind of do some kind of iterations, and also I am not going to detail of that, and finally it is basically have this give you a C code, which is basically a high level synthesis code, where you actually apply it is actually generate a hard code where actually all the optimization things are getting embedded, right. So, you just run that code using any RTL HLS compiler, and then it will you will get a efficient hardware. Okay. So, this is the tool is does objective is same, you have to parallelize your behavior, but the way this Hetero-CL does and AutoSA does is different, right. So, but this is something is more relevant if you try to do something from C, because for Hetero-CL on T2S you have to specify your language, your algorithm in the language that they support, right. But this AutoSA supports C, but it is again generate a parallel hardware. Okay. So, I have last for this three this AutoSA, this Hetero-CL and T2S, I have just taken this some few pictures from this particular tutorial by these three professors, right. So, this is their work, I just taken this diagram from their slides to explain this. Okay. So, just to conclude this, we have discussed today the recent work that is happening in the context of high level synthesis, and we have seen different areas like security, verification, and then this creating a flow from the tensor flow to RTL, and most importantly doing a temporal to spatial conversions, which is basically parallelize your C code, which is one of the very active domain of research, and where I have discussed many tool that is actually recently proposed, right. So, just as a concluding remark for this course, so we have understood that this background technique like allocation binding, this scheduling, those things are kind of mature, right. So, the tool are kind of mature. So, these are the two area where we actually the work is happening to make this high level synthesis is make is powerful tool which can generate a hardware or a RTL, which is will be equivalent to a code which can if a RTL designer write it himself, right. So, So, the two areas, what is basically converting your sequential behavior into some parallelized behavior, so that that can actually utilize the power of this high level synthesis tool, and internally this tool actually apply different kind of optimizations like unrolling, pipelining, data flow, and there are many constraints are there. So, many times this particular tool may not able to apply this because of certain dependencies or because of some constraint, right. So, the internal to the tool, if you ask me, to tool working hard, I mean try to remove some of these restrictions, in the sense that they try to automate internally, so that this kind of restrictions can be modified into some form, which so that your pipelining have efficient implementation, right. So, in the context of tool, that is where the maximum effort is going on. Specifically for the data flow, I would suggest, because in the data flow sometime if you have the code, if you just apply HLS pragma data flow, automatically it generate this kind of parallel architecture, right. So, that we have already discussed. So, and there also we have seen many kind of restrictions are there. So, how we can actually automatically analyze certain things, and I can rewrite my code internally, the tool itself, so that I can apply these data flow optimizations, right. And in the front end, because as a user, when you try to use it, I mean everybody, it is well understood that for any generic C code you won't get a hardware. So, you need to understand the way this high level synthesis works, and then probably you have to rewrite some of the code and and so that this gets mapped correctly in the hardware, right. And there we have some recent work that try to automate that process, right. So, instead of rewriting yourself, can I automate that process, right. So, that is what is the front end, this AutoSA and Hetero-HLS kind of tools are there, right. So, that is something is very interesting area, which actually reduce your effort of design space exploration, right. So, otherwise you have to try option 1, option 2, option 3 and see which is happening, which is maps to a different hardware, right. So, that is the design space explorations in context of parallel hardware is happening at the top end, right. So, these are the areas which is something is very important to make this high level synthesis tool useful for generating efficient hardware accelerator, right. So, with this comment I conclude this course. Thank you.